In this module, we're going to look at the solid state. And so we've looked a lot at liquids, we've looked a lot at aqueous solutions, but we haven't looked a lot at solids. And what we're going to find is that we define a solid crystalline structure by what's called the unit cell. And by studying this unit cell, we will learn everything there is to know about that solid structure, as these crystalline solids are repeating patterns of three-dimensional structure, and looking at the unit cell is that smallest repeating unit. And so this unit cell will come up over and over again in this chapter, as it is what we're able to study to understand the entire crystal. Here's the first of the unit cells we're going to be looking at, called simple cubic. And this is the simplest of any of the unit cells we can have, where it's a cubic cell, we have a cube, right? We only have one edge length parameter, and all the angles are 90 degrees. And for the simple cubic case, atoms are only on the corners of the cube, and they're adjacent to one another. When we look at this unit cell, we want to break down which atoms are actually within this unit cell, because if we look at each atom, it's actually not completely within this unit cell. And so the image on the right shows this truncated version where we only look at the matter that consists within this unit cell. And as a reminder, the unit cell is a repeating piece that stretches infinitely, effectively infinitely, in all directions. So understanding this unit cell will help us understand the entire crystal structure. Each corner atom is actually shared by 8 unit cells, and as such we only have an eighth of an atom within this specific unit cell. However, there's one of these atoms on every single corner of this unit cell, and therefore there are 8 eighths of atoms that belong to this unit cell. And that's 8 times 1/8, which means that there is one atom belonging to the simple cubic unit cell. Many different types of unit cells exist, and we're really only going to focus on the cubic ones here. But note that there is just a huge variety of ways that we can define solid state structure, and that it is understood, right? But for here, we're going to look at 3 different cases. Simple cubic, which we already discussed a little bit, atoms only on the corners of this cube. Face-centered cubic, where we have a different atom that's on the face of the cube in every side, all 6 faces. And body-centered, where we have an additional atom in the center of this cubic unit cell. And here are those 2 structures, right? Here's the body-centered cubic, where the gray atoms are on the corner and the red atom is in the center of the body of this unit cell. And we also have the face-centered cubic structure, where the red atom is on the face, all 6 faces here. This is 2 other cubic unit cells that we're going to look at in this video, and are really important to understanding other unit cells if you end up studying more solid-state chemistry. Okay, 3 types of unit cells: simple cubic, body-centered cubic, face-centered cubic. Again, the motivation is if we know about the unit cell, we know about the entire structure, because the unit cell represents the entire structure. So a first question is, how many atoms are even within the unit cell, right? Like, how much matter is defined in this simplest unit? And we've looked at the simple cubic case already, where there's 8 corner atoms, and 1/8 of those atoms are within each cell. This is actually the case for all 3, whether it's body-centered or face-centered, we still have these 8 corner atoms that are present. Within the body-centered, we have 1 body-centered atom, and within face-centered cubic, how many atoms do we have that are involved? Well, we have 6 face-centered atoms. But here, I think maybe try to pause the video and think about, well, can you determine how many total atoms are within each of these unit cells? Because remember, in the simple cubic case, each of those atoms is only partially belonging to the unit cell, and that may be the case for these other atoms as well. All right, hopefully you got a chance to try to determine how many atoms belong to each unit cell. Note that, again, the corner atom is always shared by 8 different unit cells. Only an eighth belongs to this cell. And to be clear about that, that's sort of 4 that are on the bottom plane, and then 4 that are on the top plane, and then this sphere sits kind of at the nexus of all of those for each of the corner atoms, and therefore just 1/8 within this unit cell. Body-centered atom, that whole atom is part of the body-centered cubic cell, and so there's 1 body-centered atom that's in the body-centered cubic cell. Face-centered atom is contained by 2 unit cells, but there are 6 of them, and therefore there are 3 face-centered atoms that are part of the face-centered cubic cell. And therefore, what we can see is that the simple cubic contains 1 atom, The body-centered cubic contains 2, a corner and a body-centered, and the face-centered actually contains 4, 1 corner atom and 3 face-centered atoms. Okay, another really big benefit of studying the unit cell is that we can understand something about density, right? Let's say that barium crystallized in a body-centered cubic unit cell, and we've actually determined the edge length of this cell to be 5.025 angstroms. Let's calculate the density of barium. And here, I'm going to go ahead and lay out an outline. Remember, body-centered cubic, right? If we know that that's the unit cell, how many atoms are there per unit cell? Let's just assume they're all barium. What's the molar mass of barium? Then kind of walk through these other ideas and see if using all that you can figure out the density of barium. So go ahead and pause the video, see if you can calculate each of these steps, and then I'll show you my answer. All right, let's go ahead and take a walk through. Body-centered cubic, this means 2 atoms per unit cell. We determined this previously, 1 corner atom and 1 body-centered atom. Molar mass of barium, this is 137.327 grams per mole. We can get this from the periodic table, right? And we're sort of starting on our way, right? We know now the mass of a certain number of barium atoms. That would be very important to know here. Now we want to calculate the mass of only the atoms within a unit cell, right? We want to constrain our study to the unit cell. How many atoms are part of the unit cell? Well, we've determined that it's 2. Now we can start with the molar mass, and we have grams per mole. We can convert that to grams per atom using Avogadro's number, and then note that it's 2 atoms per unit cell to get a final mass of 4.562 times 10 to the negative 22 grams, and this would be per body-centered cubic unit cell. This is the mass of the unit cell. Now, what about the volume? What volume does this correspond to? Well, we know the edge length, right? It's 5.025 angstroms, which means it's 5.025 times 10 to the negative 8 centimeters. Remember that an angstrom is 10 to the negative 10 meters. And then remember that it's a cube, right? So if we know the edge length of a cube, we actually know the volume of a cube. It's just the edge length cubed, and we end up with the following cubic cell volume. Again, a really small area. But now we actually have the mass and the volume of a corresponding volume, which is the unit cell. So given we have both of those, can we get the density? And the answer is yes, we can, right? The density of the cell, which is also going to be the density of this whole species, is the mass divided by the volume. We divide the two by one another, and we end up with something very close to the literature density of barium, 3.595 grams per cubic centimeter. And so this really shows that we can connect the unit cell properties, which is a microscopic study, to something like density, which is a macroscopic property of the barium. Okay, one last thing that's nice to know about unit cells is that we can calculate the packing density, and here we'll just show what the packing densities are. Simple cubic, 53%, body-centered cubic, 68%, face-centered cubic is the densest one here, 74%. And we can get this through pretty much geometry and calculating, well, if we have this cube and we have these spheres that are assembling in a certain way in this cube, how much space is occupied by the spheres? That is the packing density. Face-centered cubic is packed the most efficiently, highest percentage of occupied space, that's significant. For our last calculation, let's calculate the free space in a body-centered cubic cell. And remember here, or note, that in this case, the body-centered atom is adjacent to the corner atoms. The corner atoms are actually not adjacent to one another as we go along the edge of the unit cell, and that's really, really important. Now, you might want to pause here and see if you can solve this one on your own. It is a little tricky, but there's no real chemistry concepts involved other than understanding the unit cell. It's strictly a geometry problem. Can you define the radius in terms of the edge length of the cell? And note again that the body-centered atom is what's adjacent here. That's what's going to give you that relationship between the radius and the edge length of the unit cell. So go ahead and pause, see if you can do it. All right, let's start to break things down a little bit. So here, right, let's remember that the occupied space is the volume occupied by the atoms divided by the volume of the unit cell. Right, if we can basically calculate the volume occupied by atoms in terms of the cell edge length, we could just divide the two and we can get the occupied space. So let's assign the edge length as A. This is a very common way to determine the edge length, the common variable to use for it, and we can express the volume of the cell. If the edge length is A, the volume of the cell is just length times width times height. It's going to be A cubed. But how can we use geometric relationships to relate R to A? R being the radius of one of these atoms. Because we know there's two atoms within this body-centered cubic cell, how can we express R in terms of A so that in the end we might actually not even have a variable that's part of our occupied space. And remember here that it's on the diagonal, corner to corner, the atoms are adjacent, and we want to know how many radii this is, right? It's this that's adjacent, right? It's as we go through the middle and from corner to corner. So if this is how the body-centered atom is adjacent to the corner atoms, how many radii does this cover? And the answer is it's 4 radii, 4r, because we have 1 radius on each corner atom and 2 radii for this central body-centered cubic atom. Now we can actually make a triangle, and now we have a Pythagorean relationship that we can look at. So here the answer is going to be a root 2, and this we actually obtain by looking at the bottom face where it's a 45, 45, 90 triangle and the other 2 edges are a. We can solve that using the Pythagorean theorem as well. But with this, now we can express, well, a squared plus a root 2 squared equals 4r squared. This is another Pythagorean relationship. And we can go ahead and evaluate this as a decimal. That's fine. We're going to get a percentage in the end anyway. And we get A in terms of R, and that 0.433A is equal to 1 radius. With this relationship between A and R, that's great because what's the volume of a single atom? Well, it's a sphere, 4/3 pi r cubed, and we can get that in terms of A. If we plug in A as our expression for R, we can say, well, the volume of one of these spheres is actually 0.340A cubed. That's what we've gotten from the volume formula. How many atoms? Well, we know there's 2 atoms, and therefore the volume occupied is 2 times the amount of space that one sphere occupies, and that's 0.680A cubed. Finally, we just take the volume occupied by the atoms divided by the volume of the unit cell, which is A cubed, and that's how we get our 68% occupied. This is the same process you would use for any other unit cell. You would just have to determine your geometric relationships based on what you know. The last thing we want to talk about is X-ray crystallography, where we basically beam X-rays through a crystalline material, and these X-rays are diffracted, which are going to make a pattern that can be read and understood. And this diffraction is based on the structure of the crystalline material. And so the way that the X-rays are changed by passing through the crystalline material can reveal the structure, even the unit cell, and ultimately give you a lot of information about solid-state chemistry. X-ray crystallography is kind of the gold standard of solid-state imaging techniques and is definitely something that you will see if you end up studying solid-state chemistry further, and did just want to end on mentioning this technique and that the unit cell is actually not as far away as you may believe because we happen to have this tool, X-ray crystallography.